Hey everybody, hope you're doing well. This is the end of week 6 here in the fourth marking period. This will walk you through section 9.2, which will teach you how to write and use geometric sequences. As you recall in the last video, you learned some of the basics of sequences and specifically the arithmetic sequence. This is the other major type that you are going to learn about here in this unit. So what exactly is a geometric sequence? This is a sequence that has a common ratio amongst all terms. Common ratio is a consistent value that is multiplied or divided from one term to the next. So arithmetic sequences you learned in the last lesson, they had what was called a common difference, where the same thing is added added and subtracted. Geometric sequence, we're looking for the same thing being multiplied or divided. So what we're going to first look at here are some sequences to determine if they are indeed geometric, and if they are, identify what the common ratio would be. And then we're going to take a look at how to write a geometric sequence and in a couple of different ways, very, very similarly to what we learned and went through in the last lesson. So, 3 sequences here. Let's determine if they are geometric. So, what we're looking for is the same thing being multiplied or divided the whole way through. So if I look at number 1, this sequence is indeed geometric. The reason being, if I go from one number to the next, I am multiplying everything by -4. So the common ratio amongst all these terms is -4. Everything gets multiplied by -4. That gets me from one term to the next. The second sequence that we have here is also a geometric sequence. So the reason that is a geometric sequence is because everything is being divided by 3. Now, you'll see when we do this here in a few minutes when we have to write sequences, we aren't going to write out like a division sign in 3. We're going to write these out as fractions. So if I can divide everything by 3, it's the same thing as multiplying by 1/3. So if you see a fractional ratio like that, that means division was involved, okay? But we're going to write anything that's a division, a ratio that involved division, if you will. We're going to write it as a fraction. After all, ratios are indeed fractions. So everything divided by 3, that means it's the same as multiplying by 1/3. We're going to use that. The last one here is not geometric. We're not multiplying by the same value or dividing by the same value as we go from one to the next. This is actually an arithmetic sequence because to get from one value to the next, we simply add 2 every single time. So there is a consistent pattern, but it's addition, not multiplication or division. So this will be arithmetic, not geometric. Now, let's take a look here. If we have some geometric sequences, how we can write rules for them. So this is a different formula from the arithmetic sequence formula that you learned in the last lesson. There's a lot of similar components, a couple quick little changes in variables here, but ultimately a lot of the same components. Rule for a geometric sequence, a sub n equals a sub 1 times r to the n minus 1 power. A sub 1, just like the last lesson, it's the value of the first term. N is, once again, the position of the term in the sequence. So first term, second term, third term, N would be 1, 2, 3, etc. A sub n is the value of the nth term in the sequence, just like we went through in the last video. The only real difference here, R is used instead of D. Last lesson, D was used for arithmetic sequences because it represented the common difference. R is used in geometric sequences because it represents the common ratio. So same idea, just a change in letter. You'll notice that the formatting is certainly different for what the type of sequence is, so that in itself is probably the biggest difference. Now, the nice thing about geometric sequences, these are actually a lot easier to write because there really isn't much in the way of simplifying that you'll need to do. Arithmetic sequences, we had to distribute that common difference, combine some like terms. It wasn't that it was hard, but it took an extra couple of steps. These, as long as you have the first term in the common ratio, these are going to be pretty quick to write. So the first handful of examples here we're going to look at, here's the sequence. I tell you it's geometric. We're going to go ahead and just write the rule straight up and then go find a given term. So 3 steps here in order to write and use a rule for a geometric sequence. First thing you're going to do is identify the first term, so that a sub 1, and find the common ratio. Next thing you'll do is you'll substitute them straight into the formula. And again, once you do that, that's your rule. There's nothing you're going to have to simplify. Third step, if asked to use a rule to find a sub n, so if you're asked to find like a sub 14 to go find the 14th term, substitute that in for n and solve, just like we did in the last lesson. So we got 3 examples here. Let's go ahead and walk through them. We're going to go ahead and write the rule for each, and then use that rule to go find a sub 9. So we are going to go ahead and go find the 9th term. So we're going to lay this out very similar to the last lesson. If you paid decent attention in that first video here, you're going to see a lot of this is going to look pretty darn similar. So, first thing I want to do here is identify my 2 main pieces, my first term and my common ratio. First term in the sequence is 14. To get from one term to the next, we are multiplying everything by 2. So r equals 2. So I'm going to go ahead. So here's my formula. I'm going to go plug in the A1. And I'm going to go ahead and plug in R. Now, there's 2 ways you can technically write this, and I don't care either way. First way you can write it here, I'm actually going to write it the way that directly matches the formula. You can write it like this, no big deal. One thing though, if you're going to write it like that, do not make the mental mistake of multiplying 14 and 2. The reason why you can't multiply those together is because of this exponent. The fact that the 2 has an exponent means you cannot multiply 14 times 2 and magically turn it into 28. So, you can write it like this. If you think you're going to look at that and mess that up, the other way you could write this, and this is the way you'll probably see me write it a lot, is I'm going to put parentheses around it. It doesn't really matter which way. I'm probably going to write it with the parentheses a lot more, just out of habit. But ultimately, the biggest thing I need you to realize, do not multiply the 14 into 2. That is out of order of operations. You cannot do that. So, you stop your writing the rule there, you're done. That's what I mean by there's no simplified. Once you plug in those 2 numbers, you've got them in the right spot, you're good. So now what we're going to do is we're going to go ahead and find that 19th term, or excuse me, the 9th term in this case. 19 would be way too big. So, now we're going to go ahead and find a sub 9. So, I'm plugging 9 in for n. Now again, you can do this in a bunch of little ways with your PEMDAS, or you could plug this all in the calculator. That's up to you. But this would simplify into 14 times 2 to the 8th. And again, if you're using PEMDAS and you want to solve it step by step, make sure the exponent gets subtracted first. Then you want to do 2 to the 8th. Again, exponents before multiply. Then multiply that 2 to the 8th answer by 14. Ultimately, though, if you put this all together, the 9th term in this would be 3,584. One thing you'll notice when we find and work with geometric sequences here, if we're trying to find random terms in the sequence, you're going to get either really big or potentially really small answers. So if you have a ratio that's above 1 and you're trying to find like the 9th, 10th term, that's going to get pretty big, okay? We'll see with an example here in number 3 where we have a ratio that's under 1. That means you're going to get answers that are probably going to be really, really small. So again, don't be surprised if you get some big numbers when you work with things that are geometric. All right, let's go ahead and work with number 2. So once again, my first term is 5. Common ratio, if I multiply by 3 the whole way across, I'm going to get all those terms. So, to write my formula, all I have to do is plug in the first term, the ratio, and that's it. So I'd write it as 5 times 3 to the n minus 1 power, and that's it. Again, do not make 5 times 3, turn it into 15. That is not allowed. That is out of order in terms of operations. So, I have my rule. Now let's go ahead and find a sub 9. So, plug in the 9 for n. So again, if you want to simplify a little, that's fine. But again, ultimately, I would just punch this in your calculator using all the things that you've learned about how to enter stuff in throughout the year. You should get a result 32,805. So again, another big answer, but again, geometric sequences, you can start expecting some really big numbers there. All right, number 3. We've got the first term of 12. To get from one number to the next, so they start going downwards, so that means we're probably dividing stuff. To get from one number to the next, we're going to divide by 4. To represent a ratio of division by 4, that's the same as 1/4. So, once again, I'm going to go ahead and plug all those things in. 12 times 1/4 to the n minus 1 power. Again, I can't emphasize this enough. Do not turn 12 times 1/4. Do not do it. Do not multiply those together. Leave that alone. And that's your formula. Now, let's go ahead and find that 9th term. So, a sub 9 equals 12 times 1/4 to the 9 minus 1 power. So that would be the same as 12 times 1/4 to the 8th. Now, admittedly, I made this kind of up off the top of my head. This gives you a really small answer. If you have a common ratio, again, that's under 1, between 0 and 1, you are going to get some very small answers. Because, again, you're multiplying a fraction by itself that many times, it's going to make it incredibly small. Your answer for it, so if you plug this into your calculator, you'll probably see that magical E that a lot of you have forgotten about because you haven't had to do scientific notation in a whole bunch of years. The answer you're given is written in scientific notation. I believe it's 1.83 blah 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 E negative 4. That is a fancy way of saying 0.000183. So it wasn't really my intention to give you something that was a result that would require scientific notation. On the graded assignments on the homework, you won't see anything that gives you anything that small. But if you see in your calculator, well, what's that E mean? That just means wherever that decimal is, if it tells you E negative 4, it just means 10 to the negative 4th. You move the decimal point back 4 places. That would be your rounded answer. So very, very small term. And they continue to get smaller and smaller as the exponents were to go up. But again, that's how you write a rule for a geometric sequence and how you use the rule to go find any random term that you want. So the last part of this, kind of similar to what we did with arithmetic sequences. If I give you a random term in the sequence and the common ratio, let's go ahead and find that first term so we can actually go ahead and write the rule. So, same steps that we went over in the last video here when we had this type of scenario. If I give you a random term and the common ratio, we're going to substitute those things in first into the formula. Go find that first term and then write the formula, write the rule using the first term and the common ratio. You'll notice here it says simplify. Again, there's not really much in the way of simplification here, so we don't really need to even worry about that. So let's go ahead here, 2 examples, let's work them through. So, you know a sub n because I'm telling you the third term is negative 18. So the nth term that we're dealing with is negative 18. The n value is 3 because it's the third term. And the common ratio, also 3, because that's explicitly given to us. So once again, I'm going to write out the formula. And we're going to go ahead and plug in what we know. So again, we know what a sub n is because we know what that nth term is. We don't know a sub 1. We're trying to find that. We know the ratio. We know the exponent. So, first thing we're going to do, simplify the exponent. So again, you can put parentheses around this or not. That really doesn't matter too much. So I end up with negative 18 equals a sub 1 times 3 squared. We'll do 3 squared. That'll get me 9. Again, we're connected by multiplication, so undo it. By division, negative 2 is equal to a sub 1. So the first term of the sequence would be negative 2. Now to actually write the rule, again, all I got to do is plug in my first term, so I know it's negative 2. Plug in the common ratio. leave the ends blank because the rule represents all the possible terms we can find. And there's my answer. Negative 2 times 3 to the n minus 1 power. Last example here, same exact idea. I tell you the sixth term is equal to 324. And unfortunately here, a little typo. Again, they all kind of mean the same thing here, but to be exact, it is a common ratio. So again, we're going to use R for that. The common ratio there would be negative 3. So, again, a sub n is 324. It is the sixth term, so n is 6. And the ratio is negative 3. So once again, we're going to plug in what we know. So it'll be 324 equals a sub 1 times negative 3 to the 6 minus 1 power. 324 equals a sub 1 times negative 3 to the 5th. The one place where I could think it is a benefit to definitely use parentheses. So you notice here we have a negative ratio. We all know how negatives and exponents can be a fun adventure for a lot of you here. If you put parentheses around that negative term, you'll never have to worry if your sign is correct. So ultimately, I would, especially with a negative ratio, put parentheses around it so that gets evaluated correctly. Negative 3 to the 5th power is negative 243. So again, that's being multiplied. We divide everything by negative 243. It will spit out a decimal. I would recommend, you could technically write it as a decimal. It's not super wrong. But the most accurate answer, it's actually the fraction negative 4 over 3. And that's equal to a sub 1. So the first term would be negative 4/3. Now that I have that, I've got my first term, I've got my ratio, I can go write my formula. So a sub n would be equal to negative 4/3 times negative 3 to the n minus 1 power. And that is my final equation. So again, hopefully in walking through this, you see a lot of similarities to how we work with arithmetic sequences. It's just a different formula. The formatting is probably the biggest difference between what we did in the last video and what we're doing in this one. So once again, great assignment for this. It's going to look very similar to the last one that you completed. 6 questions, again, basically 2 of each thing that I just walked you through. Extra problems, the practice and the quote-unquote homework. So again, if you need to try some before you do the graded assignment, please feel free and then go ahead and check your work. So once again, if you have any questions on anything, send me a message on Schoology, shoot me an email, or feel free to stop by my office hours on Zoom, and I'll be happy to help you out as much as I can. So once again, thanks for watching. Stay safe, stay healthy. We'll see you next time.